Yeah. First of all, I'd like to thank the organizers for the invitation. Yeah. Today, I would like to talk about some connection between Debye equation and positive curvature on vector bundles. Yeah. So one is in the side of TDE. Yeah. Another side is in differential geometry. So first of all, let me recall some basic concept in mathematics. Yeah, the so-called Breuer subharmonic function, which was introduced by Orca and Lalonde separately in 1940s. So this function is defined as an upper semi-continuous function. Maybe take the values minus infinity, yeah, which this when restricting on each complex line, it is a subharmonic function. So here we consider the polar set as the singularity of the Breuer subharmonic function. So the typical example is given by this formula. So here F1 and Fk are holomorphic functions. So you know when F1 Fk is 0, so this is the so-called analytic subset. So analytic subset is a special case of this Breuer subharmonic function singularity set. So when the function is smooth, so and even strictly Breuer subharmonic function, so you get the potential of Kähler form, Kähler metric. So for example, Bergman metric, yeah, the potential is just smooth Breuer subharmonic function. So in this way, we can define singular Hermitian metric on holomorphic line bundle. So locally, so the metric is given by E minus phi. So phi may be not necessarily smooth, just locally integrable. So in this case, we can still define the curvature, yeah, in the sense of currents. So by dt bar phi. So we can define a pseudo-effective line bundle. So this means this curvature current is positive. That is to say, phi is Breuer subharmonic. And you can still define a big line bundle. So this means the curvature current has a positive lower bundle. Yeah, so this means has a positive lower bundle. Omega is a Kähler form or Hermitian form. And the more special case, so the so-called, yeah, the positive line bundle. Yeah, so in this case, this means phi is smooth, strictly Breuer subharmonic function. So of course, we have such relations between positive amplities and the semi-ample, semi-positive, and the left and the pseudo-effective. So pseudo-effective is a more general concept. So as you know, Kodaira vanishing theorem says that if the bundle is a positive holomorphic line bundle, then we have this vanishing theorem. So this is the canonical line bundle. So using Kodaira vanishing, you can get the embedding theorem. So this means positive is ample. So actually, in compact Kähler case, people consider omega Breuer subharmonic function, yeah, and also singular Ke. So So in the many important functional K-energy, the definition domains, when you do completion, so you get general Pareto subharmonic function, maybe singular, yeah, and maybe not smooth. So you can naturally define an order, yeah, and the equivalence of the singularities. So given two Pareto subharmonic function, phi is more singular than psi. So this means we have this inequality. So you can define two Pareto subharmonic function have equivalent singularities. So as you know, very classical invariants, for example, Reynolds number, yeah, a Pareto subharmonic function at some point. So this number is defined by this formula. And you can also define a higher Reynolds number, so the so-called J's Reynolds number. So this is defined by this mass. So in particular, so Reynolds number is the nth Reynolds number. So you can also define a complex singularity exponent. So in algebraic geometry, this is called LCT. So this is defined by the supremum of such real numbers, yeah, such that this exponential, this function is locally integrable at this point. Yeah. So recently, we introduced the following concept, LTT. Yeah. So this number is given by this formula. So we take infinite limit. Yeah. So when this number is finite, yeah, we can get this inequality. Yeah, for such beta, this is non-negative. The sum is 1. Then we have this inequality. So in particular, if V1 is 0, yeah, yeah, yeah. So yeah, V1 is the Reynolds number. Yeah, yeah. So this is the Reynolds number. So we can get the zero mass, complex Monge-Ampere mass is 0. Yeah. So in this under this condition, so we can, in this case, we can solve the zero mass conjecture. So another invariance is the so-called multiplier ideal sheaf. Yeah, so this means given a Pareto subharmonic function, we have an ideal subsheaf which consists of gems of holomorphic functions such that this function is locally integrable. So of course you can define the multiplier ideal sheaf associated to a pseudo-effective light bundle. Yeah, this is a singular metric. Phi is just Pareto subharmonic. And replace 2 by p, you can get LP multiplier ideal sheaf. We have some very basic properties of multiplier ideal sheaves. So Lado proved that such a sheaf or multiplier ideal sheaf is coherent. So using this theorem, you can give a very simple proof of the statement local integrable point set of this function is analytical set. So the argument is as follows. So since this point set is just the zero set of the multiply ideal sheaf, and the zero set is the support of the Cauchy sheaf. Yeah. So this since multiply ideal sheaf is coherent, so the Cauchy sheaf is also coherent, and the support of a coherent sheaf is always analytical set. So this theorem was proved by Pompili. Yeah. But using this result, you can give one sentence proof. And another theorem is that multiply ideal sheaf is integrally closed. And the Ladle has the following vanishing theorem. So if this Lie bundle is a big Lie bundle on a weakly pseudo-convex Kähler manifold, then we have this vanishing theorem. Yeah. So this theorem, yeah, was formulated by Desmailly. So here this multiply ideal sheaf actually is associated to this Lie bundle. Yeah. So in particular, when phi is smooth, yeah, when phi is smooth, so you, of course, this sheaf is trivial, so you get Kodaira vanish. And from this theorem, you can also prove the Kawamata-Fieldberg vanishing theorem in algebraic geometry. The Kähler condition in this theorem could be dropped. Yeah. So with my former student Meng, we proved that if X is holomorphic convex manifold, yeah. So maybe not Kähler, so we can still get this vanishing theorem. By Ladle vanishing theorem, yeah, multiply ideal sheaves could be used to give a unified solution to a Levy problem solved by Orca Grout for complex manifolds in several complex variables. Yeah. So this means Grout's solution means Kähler exhaustion implies steightness. So Kähler exhaustion means the existence of a Kähler metric with global exhaustion potential. And you can also give a proof of Kodaira embedding theorem in algebraic geometry, I just mentioned. So in this way, several complex variables and algebraic geometry come together. Another property was conjectured by Desmailly. Yeah, he has the following strong openness conjecture. So the statement says that the asymptotic multiply ideal sheaf is just the multiply ideal sheaf. So asymptotic multiply ideal sheaf is defined as the union of these sheaves. Yeah. So by the strong lottery property, you can take locally. You can take some positive number such that we have this equality. Yeah. So actually, so we have the following equivalent reformulation. Yeah. So one is as follows. So the conjecture is equivalent to say if this function is locally integrable, so there exists a positive lambda such that this function is still locally integrable. And another reformulation is that this real lambda set is actually open and interval. So this is an open interval. So actually, the very basic origin comes from calculus. In calculus, this function, this function is locally integrable. Then you can get some bigger p such that this is still integral. So a famous result was proved by Bob Benson. So this is the so-called openness conjecture. So if this function is locally integrable, so that is to say this multiple ideal shift is trivial. So this was proved by Bob Benson. Actually, this conjecture was stated many years ago. Recently, I read a paper given by Gisman. In his paper, before Demai, Gisman already posed this conjecture. And in two-dimensional case, so the stronger openness conjecture was proved by Barry, Johnson, Mustard in the papers. So our result is as follows. Demai's stronger openness conjecture is true. And in the same paper, the same proof is used to prove the following two forms. So this means a sequence of Fourier subharmonic function, increasingly convergent to a Fourier subharmonic function. You still have this equality. And another form is the following. So phi and psi, both functions are Fourier subharmonic. So you can still have this equality. So this the proof. The paper was published in 10 years ago. And our proof is based on our study of a series of papers on the optimal two extension and its geometric meaning. So this geometric meaning was stated in our another paper, with my former student Guan and with Zhou for Keller case. So the geometric meaning was used in the study of Itaka conjecture and the singular positivity of high direct image by Takayama. And recently, BDPP's unirulist criteria for Keller case. BDPP is for projective case. Recently, our colleague O gave a generalization to Keller case. So actually, using the stronger openness, we can get the following corollary. So actually, this function is convergent to this function in locally L1. Yeah. So the argument is as follows. So by the strong coordinates, you can get some J0 such that this we have this equality. So in particular, so we have this finite integral. But this function is dominated by this integrable function. So we are done by dominated Leiberger's dominant convergence theorem. Another corollary is the following vanishing theorem. So here we can consider a pseudo-effective Lie bundle. Yeah. So in this case, we can define numerical dimension of this singular pseudo-effective Lie bundle. So we can get this vanishing theorem. So for any Q is bigger than this lambda. So in particular, when this bundle is big, then the numerical dimension of this bigger bundle is just n. Yeah. So in this case, you reduce it. You reduce the theorem reduces to Leiberger's vanishing theorem. So another corollary is as follows. So for a big Lie bundle, so we have this equality. So this is a conjecture by Desmailly, Lawrence An, and the Lazarus field. Yeah. So you can find the problem in Lazarus field's book, Positivity in Algebraic Geometry. So the meaning of this symbol. So this is the so-called asymptotic multiply ideal. So this is the maximum member of the family of the ideals. Yeah. So this is given by the linear system. And H mean is guaranteed by Desmailly's theorem. So for any pseudo-effective Lie bundle, then there exists a unique up to equivalence singular Hermitian magic with minimum singularities. So H mean. So by strong coordinates we can get this two multiply ideal sheaf are equal. So strong coordinates is used recently, yeah, in important papers to give new approaches to Yeltian Donaldson conjecture. Yeah. So for example, in Berman Bookson Johnson's paper, yeah, and also Davos Zhang also discuss a general set. So X is a compact Kähler, and anti-canonical bundle is big. Yeah, here not necessarily positive. Yeah, if this is positive, so this is the so-called Fallon manifold. So as a starting point by Davos Zhang is, yeah, then introduce lambda D function. Yeah, D functional is suitable for algebraic case. Yeah, but for Kähler case, yeah, then introduce lambda D functional. Yeah, so here lambda, the existence of lambda is guaranteed by the strong coordinates. And we'll also discuss some stability property. Yeah. So the setting. Yeah. So phi j is still a sequence of some Breuer subharmonic function, convergence to phi. Yeah. In particular, if phi j is not bigger than phi, we have this inclusion. So we also let the multipliers also changed. Yeah, so we consider a sequence of multipliers, yeah, holomorphic functions, yeah, normally convergent to a holomorphic function. Then we can still have, yeah, these functions is also convergent to these functions. This function in log one norm, yeah. So in particular, you can get a semi-continuity of the complex singularity exponents and the weighted LCT. Yeah. So the proof is based on my joint paper with Guan in 10 years ago, a paper, yeah, 10 years ago. So now let me recall some fundamental theorems about two existence theorem. So actually, Homander two method using PSH weights. So actually, PSH Breuer subharmonic function weight could be regarded as a singular metric on trivial Lie bundle, such that the bundle is pseudo-effective. Yeah. So for example, for simplicity, we recall his result. So D is a banded pseudo-convex, and the phi is a Breuer subharmonic. So you can solve this Debye equation with L2 estimate. Yeah. So this is a weighted estimate. So here phi, yeah, is any Breuer subharmonic function. Yeah, not necessarily smooth. Yeah, yeah, and this may be singular. So this you can regard the L2 Homander's theorem is for Lie bundle. So now let me recall Demailly's extension for vector bundle. Yeah. So let's recall some basic concept in holomorphic vector bundles. So you can consider a Hermitian holomorphic vector bundle. So you get the unique chain connection. So you can define the chain curvature. So locally, the chain curvature is given by this formula. Yeah. So this is a local coordinate of x, and this is the frame of the local frame of the vector bundle. So you can get a natural Hermitian form on tangent bundle tensor, the vector bundle. So you can define Lacalo positive. So this means this is positive for such section. And you can also define Graves positivity. This is defined by this inequality. So Kc is a tangent vector. S is the stock of the vector bundle. So of course you can define the negative and in the sense of Lacalo and the Graves, yeah, by taking the dual. So now let's recall Demailly's L2 existence theorem. This is for vector bundle. Yeah. So we consider a Calo manifold. Yeah. So we yeah. So here this omega may be not necessarily complete. but X equipped with some complete color. So we can consider the Hermitian vector bundle of rank R. So there is a very large curvature operator. So it's given by, this is chain curvature. Yeah, this is the adjoint of L omega. Yeah. So if this operator is semi-positive on this E volume NQ form, then we can solve the D-bar equation. Yeah, so with this solve the D-bar equation with the L2 estimate. Yeah, with this L2 estimate. So in particular, when E is light bundle, you can get Hohmander's to existence. With my former students, we discuss the convex aspects of L2 existence and L2 extension. Yeah, in higher dimension. Yeah, so in one dimension case, I think this was already done by Bob Benson. Yeah, for one dimensional case. Yeah. So in these papers, yeah, we consider the convex aspects. Yeah, and later on, Japanese young mathematicians Hosono Irayama also got some important results. So now let me mention a convex of L2 Osawa Takegoshi's L2 extension. Yeah. So now this weight, maybe we don't know if it is Breuil subharmonic. So we consider any upper semi-continuous weight. If this L2 extension holds, so this means in particular when P is 2, so this means L2 extension from one point, holds, then we can get this weight function is Breuil subharmonic. Yeah, as you know, if phi is Breuil subharmonic, then we have this L2 extension. Yeah, so this is the famous Osawa Takegoshi's L2 extension. And for vector bundle case, yeah, we can also consider the convex. Yeah, so if this this is a vector bundle, yeah, if we still have L2 extension, so we can get some positivity for this vector bundle. So in the case of light bundle, so this means phi is Breuil subharmonic. And we also discuss the convex of L2 existence theorem. So we say a Hermitian holomorphic vector bundle is L2 optimal. So this means locally we can solve this D-bar equation for L2 existence theorem with this L2 estimate. Yeah, with this L2 estimate. So our result is as follows. So for smooth metric, so this is L2 optimal. So this means we can solve the D-bar equation with L2 estimate locally, if and only if this metric is Lacaro semi-positive. So as you know, if H is Lacaro semi-positive, so this is due to Hohmander and Desmailly. Yeah. So we got the convex of the two existence theorems. So using this theorem, we can get an application, to solve a problem of Lampert. So for example, you can see in this paper we already wrote the solution of Lampert's problem. So this problem asks whether Hermitian metric, which is convergent by an increasing sequence matrices of Lacalo semi-positive Hermitian matrices, is still Lacalo semi-positive or not. So you can find. So this problem was posed by Lampert in this paper. So using our characterization, we can get the following argument. So by L2 existence theorem, so Hj is Lacalo. Then we can solve D-bar equation with L2 estimate locally. This is by Hermander Desmaillet's L2 existence theorem. And the interesting place is as follows. The L2 optimal, the property being L2 optimal, is preserved under the limit process. So actually, so this is so you can get if this is Hj, this is Hj, and you get the solutions, and here this Hj, but in this way you can take limit, you can get for the limit metric, we can still get, you can solve this D-bar equation with this two estimate. So the limit metric is still L2 optimal. So then using our characterization, so H is Lacalo semi-positive. So now we already discussed singular metric on Lie bundle and also some positivity on Lie bundles. So it's well known that this concept was extended by to the vector bundles. People also consider positivity on vector bundles. So for such a case, so you can still define multiple submodule shifts. So now, so it's natural to ask if these shifts still has some analog properties for Lie bundle. So, for example, strong openness and stability. So now let's recall some singular metric. So metric on vector bundle. So singular Finsler metric means we have this function. This function is not smooth, maybe not smooth. Just measurable. With the homogeneous property, and the zero set and the pole set, these two sets are of measure zero. So we can say this metric is singular Finsler. Furthermore, you can define singular Hermitian. So this means you have a inner product, and of course this is also measurable Hermitian metric, such that this is Hermitian semi-positive, minus this zero measure set. So for smooth Hermitian metric, we have the following equivalence, these statements. So this metric is called Graves semi-negative, and this function is purely subharmonic for any locally holomorphic section. So H is the metric, and the log is also purely subharmonic. So actually, this is equivalent for smooth metric. So in this way, one can define the Graves semi-negative and the semi-positive for singular metric. So you can define using the equivalence. So you can use this function is really subharmonic. Then you can say this metric is a singular Graves semi-negative. And by taking the dual, you can get Graves semi-positive. So using our characterization, you can define Lacaro semi-positive for singular Hermitian metric. So for example, you can see Ilayama's paper. So this means H is a singular Graves semi-positive, and H is L2 optimal. As you know, L2 optimal could be defined for singular metric. So for singular Hermitian metric on vector bundle, you can define multiple submodule sheaf. So this means this sheaf consists of gems of the stock of this sheaf, such that this is locally integrable. So in particular, if this is a Lie bundle, so this is just a multiple ideal sheaf. Hosouro and Ilayama prove that this multiple submodule sheaf associated to a singular Lacaro semi-positive Hermitian metric is coherent. And with my former students, Liu and Yang, we proved that the multiple submodule sheaf still satisfies strong openness and stability. So the meaning is as follows. So if we have this in the singular meaning, so if we have this convergence, then we get this equality. So in particular, so this sheaf, asymptotic, is equal to the multiple submodule sheaf. So here, determinant of the metric plays an important role. This was pointed out by Rolfi. So Rolfi gave some important contribution to singular Hermitian metric on vector bundles. So you can also get the stability. So we let the multiples also change. We consider this convergence. So we can still get this function is convergent to this function. locally in LP locally. Yeah. So now let's recall some well-known result, Lebourgeois isomorphism and the Kobayashi Ochiai theorem. So here we consider here Hermitian this holomorphic vector bundle. So we can consider the projective with the bundle. Yeah. And you get the tautological light bundle. Yeah. So we have the induced projection from this bundle to the manifold. So it's well known that we have this equality. Yeah. So the direct image of this M's light bundle is equal to the symmetrical power of this vector bundle. So Kobayashi Ochiai proved the following isomorphism theorem. Yeah, we have this equality, and we have this cohomology group is equal to this is for vector bundle. Yeah, for vector bundle. Yeah, volume in vector bundle. Yeah, to the light bundle cohomology. Yeah, we can. This is the Kobayashi Ochiai's isomorphism theorem. And on the other hand, Lebourgeois got the following isomorphism. Yeah, also this holomorphic. This is the sheaf of holomorphic P form. Yeah, so this is a vector bundle, volume in vector bundle, and so you can get this is a light bundle. This is a light bundle. Yeah, so your E volume, PQ double cohomology is equal to this light bundle case. Yeah, volume in light bundle. So actually, you using this theorem, you can get Lebourgeois vanishing theorem for ample vector bundle. Yeah, for light bundle case, you know this is the so-called Kodaira, Akizuki, Lakaro vanishing theorem. So you can also consider a singular Hermitian metrical case. Yeah. So if this is a singular Griff's semi-positive, and this is light bundle. We have a lateral singular light metric. So if this is singular Griff's semi-positive, yeah. So we can get the following generalization. Yeah, so we consider holomorphic vector bundle and with a singular Hermitian metric. Yeah, this is the so-called, in the sense, the strongly Lacalo semi-positive. And on one hand, we have the following generalization of Kobayashi Ochiai. So here is the symmetrical power. This is multiple submodule sheaf. Yeah, and this is for light bundle multiple ideal sheaf. On the other hand, we have the following Lebourgeois isomorphism. Yeah, Lebourgeois isomorphism. So here we have some singular metric and multiple submodule sheaf. So we get this isomorphism. Yeah, so we can reduce the vector bundle K cohomology to line bundle cohomology. So in actually in our theorem, we prove the theorem, yeah, when there exists a smooth function such that this metric is strongly Lacaro semi-positive. So of course, if H is smooth, then multiple submodule shifts become trivial, and the above theorem reduces to Le Bourdieu isomorphism and Kobayashi Ochai's isomorphism. So our proof is different from Le Bourdieu's and also Schneider's. Schneider also gave a beautiful proof of Le Bourdieu's isomorphism. With my former student Zhou, we get pseudo-effective, an injectivity theorem for pseudo-effective line bundles on holomorphically convex manifolds. So we may get a Keller type injectivity theorem for strongly Lacaro singular positive vector bundles. And using Kawamata-Fiveg-Lado type vanishing theorem, I just mentioned, for pseudo-effective line bundle, we can get a similar vanishing theorem for this singular vector bundles on compact Keller manifolds. And Bolavero obtained Desmahis type holomorphic Morse inequalities, tested with multiple ideal shifts. He discussed a singular metric case for Desmahis holomorphic Morse inequality. So in this way, one can get a singular holomorphic Morse inequality for holomorphic vector bundles. And also using Davos shell is a asymptotic formula for the volumes of pseudo-effective line bundles, we can obtain a similar asymptotic formula for the volumes of these Graves singular positive vector bundles. I stop here. Thank you very much.
Thank you very much. Any questions?
For your theory of the singular metrics, you can develop this more general for torsion-free sheaves on singular spaces also?
Good question. We do something, but I think this is still under consideration. Some torsion release.
Questions?
So for this invariant LT of pointwise singularity, do we have a good understanding when it is finite and when not?
You mean our concept LTT?
Yes.
So up to now we checked it. Up to our knowledge, all cases for zero mass conjecture, yeah, all these cases satisfies LTT is finite, yeah. Yeah, for example, invariance, torus invariance, and yeah, some result by Li Long or his joint authors, yeah. Yeah, up to now, yeah, we check. But of course, we still don't know, yeah, when this number is infinite, yeah, this is more difficult, I think, yeah.
Okay. Other questions?
I have a follow-up question to the previous question. So under the same condition, do you know of examples of plurisubharmonic functions that satisfy this condition and are not analytic singularity and have no symmetry?
Yeah. There is, you mean LTT is
Yes, so
for
one of the
yeah. We have such an example. Yeah.
yes, because as you said, most pretty much all the examples considered in the literature either have some symmetry or have analytic singularity type.
Yeah.
And for those, the conjecture is now.
Yeah.
Okay, maybe I'll follow it up with you later. Thank you.
Thank you.
Oh. Okay, let's thank Professor Zhou again and all speakers in our session.
Thank you.
So dinner is in A4, and then there's also the night